So now we were going to do that same integral and ideally get the same answer by using the Riemann sum definition. So again, that's integral from a to b of f of x dx equals the limit as n goes to infinity of our summation k equals 1 to n f of ck delta x. That's a fun one. All right, a lot going on. So yeah, there is a lot going on, but I'll show you a method here that we can use to break this down step by step. Just focus on one thing at a time, and hopefully that'll make things easier here. So yeah, we're doing our integral here. A is 0 and b is 6, so we see those on the limits of integration. 4 minus 2x is our f of x inside there. And x, doing things with respect to x. So we're going to break that down in terms of the limit of our Riemann sum. Now, thankfully, those Riemann sum values, we're using some default settings for that, so that is going to help. I do see there's a question in the chat there. Yeah, it should be 16 from 4. Did I write something down wrong? Yeah, so I didn't subtract 12 from 4. I did subtract 16 from 4 because 16 was negative area and 4 was positive area. Negative 12 was the result. Yeah. Yep, negative area versus positive area. Positive 4, negative 16, combining those together gives us negative 12. Yeah. Okay. So yeah, we're gonna look at our Riemann sum pieces here, and going in this order will help you to break things down. Step 1 is to start with one of the smaller things here, finding delta x. And question in the chat for the subtraction. No, you don't have to do it in that order. You could take negative 16 and add 4 and end up with the same result. But don't make 16 positive because it's still below the x-axis. So no, you don't have to do it in that order, positive plus negative. You could do negative plus positive if you like. It is addition, so you can switch it up. All right. So in finding delta x, we're going to use our default formula here. For delta x, that's b minus a over n. And b here is 6, a is 0. And we are not going to put in any value for n here because n is, remember, like the number of rectangles we're adding up here, and we're going to let that n go to infinity. So we want to keep n in there. Okay, so what we get for delta x is just the expression 6 over n. All right. But now we can use that. We're going to build piece on piece here. So first you find your delta x. That's going to make it a lot easier for you to find the ck's in the next step, the right endpoints. That was our default setting for that Riemann sum. Okay, so our formula that we had for those ck values, finding the right endpoints, was to go a plus k times delta x, or a plus k times b minus a over n, but we already did that b minus a over n part, so we'll just put in what we had just found for delta x. So ck is going to be a, which is 0, plus k times 6 over n. And k doesn't have a value here either. Notice how k is our index on our summation. So that's just counting through the rectangles. So like k equals 1 is the first rectangle, and then k equals 2 is the second rectangle. And we're adding up ultimately an infinite number of rectangles. So we're leaving the k in here as well. So we just say this is 6k over n. All right, so there's our ck values. Now we're going to keep building outwards here. So we've found delta x, we found the ck's, and those ck's need to get plugged into the function so we can get f of ck. And that's our next step here. Okay, find f of ck. Okay. And our function f of x is the 4 minus 2x, our integrand, 4 minus 2x. So f of ck would be 4 minus 2 times ck. But we just found our expression for those ck values. So we are going to put that to use. F of ck is f of 6k over n, because that is what we found ck was. So we have 4 minus 2 times 6k over n. All right, be 4 minus 12k over n. All right, so now we've basically found everything inside the summation part here. We have delta x and we have f of ck. And so we can set up our sum here in this next portion. Set up the sum and the limit that we're going to need to take. All right, so I'm just basically rewriting this definition from right up here, but now I'm going to plug in what we've found for delta x and f of ck. All right, so let me see how to best write this here. Yeah, we're going to need a lot more space. Okay, integral from 0 to 6 of 4 minus 2x dx equals, I'm just going to write this down here, integral 0 to 6, 4 minus 2x dx equals the limit as n goes to infinity of our summation k equals 1 to n, and here's where we get to put the new stuff in. So putting in for f of ck, we are going to have this expression right here, 4 minus 12k over n. Okay. And then for delta x, we're going to plug in our delta x expression right here, the 6 over n. All right, so right there. And that is what we're going to have to evaluate. So good times, good times. We are going to need a fair amount of space for this. So I'm going to zoom out and move this next page or two down. Going up here. Okay, there we are. All right, so we've set up our sum and limit. And now step 5 is going to be to evaluate that sum and limit. And while this is good stuff, good work that we've done up to this point, step 5 is really the one where everything happens. So in evaluating the sum and limit, we are taking the limit as n goes to infinity of the sum. So we're going to need to do the sum first and then take the limit of that result. And in doing this, it's going to be helpful to know the properties and algebra of finite sums from section 5.1. So let me just flash those up real quick. Section 5.1 here. Oh no, that was section 5.2 where we did the summation things. Yeah. All right. So yeah, it was right in here. Knowing our constant multiple rules, sum and difference rule, constant value rule, those are going to come up in this process, definitely. So knowing that we can pull constants out to the front of a sum, that's going to be helpful. And knowing that we can separate sums, that's going to be helpful, that type of thing. So know those properties and also know our summation formulas down here, the little Gauss formula for adding up the first n integers. And then these guys I would always give to you if you need them, k squared and k cubed. Those formulas as well could be helpful. Okay, so let's go back over and see how exactly we're going to use that here. All right. So yeah, the first thing we can do when evaluating this is to notice that this term right here, the 6 over n, when it's sitting inside the summation like that, the thing that's variable inside our summation is actually not n, but k. K is the thing that's changing. So k goes from 1 to 2 to 3, etc., all the way up to n. In terms of a summation, remember n, the number on top, is just your stopping point. It's just some number. That's where you stop. So n is effectively a constant when we're looking at just the sum part. So here, n is effectively a constant inside the sum, or the summation. Okay, because yeah, n is just like some value as far as the sum is concerned. It's not changing. K is changing. So this 6 over n is also effectively a constant because n is a constant and then 6 is a constant there. So 6 over n is a constant, and we can pull it out of the sum. Okay, that is the constant multiple rule from summations. Constant multiple. Section 5.2. Okay, so yeah, this is effectively a constant and it's multiplying our other term in there. So we get to say that this equals the limit as n goes to infinity of 6 over n times our summation, equals 1 to n, with just the 4 minus 12k over n left inside. Okay. Now we get to use another summation algebra property here, because inside our sum, we have two different terms that are being subtracted. We have 4 minus 12k over n. Okay, so that's going to be our difference rule type of thing. Okay, so difference rule. Did I call it the difference rule? Let's see. Difference rule, difference property, something like that. Yeah, difference rule right here. So we're subtracting something inside our sum. We're going to be able to separate that into two different sums and subtract those instead. All right, not 5.4, 5.3. So yeah, that's our difference rule. And we can separate into two sums. Okay, so that now, give yourself a little space, is going to look like this. We got to keep writing our limit because we still haven't even touched that at all. But we're going to have a sum, k equals 1 to n, of just 4. There's our first term. And then subtract another sum, k equals 1 to n, of 12k over n. Okay, so why that turned out to be nice here is that the first sum right here is the sum of just a constant value, which we have a formula for that because 4 is a constant and that's the only thing inside that summation. Constant value. Okay, which from section 5.2 was right here. Constant value rule. Notice that saying k equals 1 to n was necessary on this. Hey, section 5.3 is why we were defaulting to k equals 1 so much. So inside our sum that we're looking at right now, the c value is 4. So we get to replace that with n times 4. Okay. And let's do that. Okay. So let me rewrite what we had outside. We're still needing to look at our limit later. And we still have this 6 over n, but this constant value gets replaced with n times 4 or 4n. N times 4. Okay. And then when we're subtracting the second part over here, we could say that this is also the same as the summation k equals 1 to n. We could say this is 12 over n times k over 1, right? That's the same thing inside there. But then 12 over n we can treat just like we did 6 over n in our first step. 12 over n here is effectively a constant inside that summation. I need to make sure that's an n right there. Okay, so constant multiple again. All right, so we get to pull 12 over n outside of the second sum. We get to put it in front like this, 12 over n times our summation, k equals 1 to n of k. All right, so we're just changing one little piece at a time here, mostly based on things that we saw in section 5.2. Okay, so let me rewrite most of this and we'll change our next little thing. Okay, we've still got this 4n, 12 over n. Now this part right here, this summation is something that we saw in section 5.2, and that is not one of our algebra properties. That is our little Gauss formula, the sum of the first n integers. We have this highlighted piece right here written exactly the same now in our section 5.3 sum. So we're going to replace that with Gauss's formula, n plus 1 over 2. Okay, so let's do that. All right, so that guy gets replaced with n plus 1 over 2. So yeah, this is the whole Gauss formula. All right. And so notice now at this stage, we've managed to get rid of all the summation symbols. That's one of your goals here, is to try and get rid of all the sums by replacing them with other formulas. And we've done that now. So that's pretty nice. We've simplified this a fair amount. And now we're going to simplify further. Okay. We're going to do some simplification here. Mostly of our fractions, because we got n and n that we could cancel, and 2 would go in 6 times up here. So we have limit n goes to infinity, 6 over n, and we have 4n minus, that got canceled out except for 6, and this got canceled out except for n plus 1. Sweet. It's getting smaller and smaller. That's good. Let's distribute here. All right, so we'd have 4n minus 6n minus 6. Okay, for this portion. So that means we have the limit as n goes to infinity of 6 over n times, that would be negative 2n minus 6 inside there. Okay, and let's distribute again. We're going to take the limit as n goes to infinity, and that would be, well, the n's would cancel there, so we would get negative 12, and then minus, that would be 36 over n. And now all we're left with is taking the limit. Okay, so it's been a little while since we've done a limit going to infinity, but remember, as n goes to infinity, this first term will be unaffected. There's no n there, all right? But the second term, yeah, 36 over n, as that denominator gets really, really huge, that second fraction there is going to go to 0. We saw that a while ago. All right, so as n goes to infinity, 36 over n goes to 0. So we end up getting negative 12 minus 0 and negative 12 for our limit there. Yeah, Felipe had it. Negative 12 is the result. Negative 36 over n goes to 0. Nice. All right. So yeah, we get negative 12 out of all of that whole long process. And so notice back here when we were setting up our sum and the limit, we said that the integral would equal the result as soon as we evaluated this sum and limit. And so now that means we've gotten our result for the integral. So the integral from 0 to 6 of 4 minus 2x dx, that equals negative 12. And that is good because that checks out with our first part of the problem where we did this with net area. So that's really good.